In this video, we're going to talk about nested quantifiers. So we talked about quantifiers in section 1.4. That's the idea of for all or there exists. Nested quantifiers mean we're going to be working with more than one. And the word nested is kind of implying that the order matters. So let me give you an example of nested that you have definitely seen before in your math. Um, Composition of functions, like if you have f of g of x, or I could also write that with the open circle, f composed g of x, okay? This means something, and the idea is that the order of this matters. So the order with which we write it actually changes how we approach the problem. And then we have this concept of that we are taking one function, and the first function is indicating which function we're plugging into. So this order is kind of telling us how to work it out. So let's look at this when we are working with more than one quantifier. Okay, so for this first example here, I just gave you the example and we'll just talk about it. So for every real number, every real number has an inverse. So how we could write that is you start with, you're talking about every real number. So we start with for all x. So for every x that's out there, where x is a real number, right? That's the domain, they're real numbers. For all of the real numbers, there is a y. So we've already categorized that every real number we're talking about, if we pick one of them, there's a y out there such that when you add them together, you get 0. Okay. That is the concept of inverse. Now they're using additive inverse. They've assumed additive inverse, which is why they said x plus y equals 0. But yeah, that's how you would write it as a nested quantifier. So they also mentioned that you could think of it as propositions, which can get a little bit messy. But here's, you would have to kind of say q of x is the idea that there exists a y for p of xy. It does get a little bit embedded. Complicated. We'll look at more of those. I think examples are really important when we start seeing that. But let's move on. Now, I pulled this right from the text. Well, I did edit it, so it's a little bit cleaner. But the idea of nested loops has a lot of applications in computer science. So when you are checking to see if this statement is true, that means you have to go and check every single one, every single x and every single y. And the minute you find that it's false, the whole thing shuts down. I think a lot of computer science people understand that. It's like a testing, right? Now, if you're working with the there exists, all right, that means then that the minute you find the one that makes it true, you can stop. So there's this concept of for all versus there exists, and this idea of nesting loops and testing. Okay, I'm not going to really belabor that. What I'd rather do is kind of look at some examples of this and allow us to understand what they're talking about here. Okay, so let's say that we're talking about all real numbers. Okay, so what we're looking at is all real numbers. Let p of xy be this statement, that x plus y equals y plus x. So here's how we would write that with nested quantifiers. So you would say that for all x and for all y, p of xy occurs, that x plus y equals y plus x. And here's how we could actually prove this statement. To prove this statement, we would have to look at for all y and for all x, p of xy. We'd have to reverse the order with which we look at the nested statement. And as long as these two have the same truth table, which they would, then this statement would be 100% true. So These two are equivalent statements, and that's how we know this to be true. Okay, so let Q of xy be the statement x plus y equals 0. Okay, so that means that for all x, there exists a y where Q of xy is true. Okay, that is what this statement says. But that would not be the same thing if we swapped the order. If I put there exists a y for all x, so there's a y out there, which with whatever number you pair it with, Q of xy occurs. All right, there's no real number out there that we can pair every real number with and add them together and get 0. Okay, it's impossible. So this is false. So switching the order up here, these ones work. Those ones came out true. But down here, this one is the only one that comes out true. That one does not. So the order with it, which it's written, does matter. Okay, let's explore that a little bit further. Oops, I'm sorry. Again, assuming that we're talking about real numbers, here's our new statement, x times y equals 0. Okay, so understanding that, let's see which statement happens to be true, okay, or false. And it's possible it could be more than one, true or false. Okay, so for all x, so we're looking at every real number, and for every y value, when you multiply them together, you get 0. That's false. That's false. Because I just have to pick any y value other than 0, and it's not going to work for all x, all real numbers. Okay. Okay, for all x, there exists a y. So for all real numbers, there exists another real number such that when you multiply them together, you get 0. That's true. That makes sense. Because when we look at all the real numbers, we can find another real number that when we multiply, we get 0. In fact, that other number is 0 itself. Okay, this one, there exists an x. So now we're picking a specific x such that for all of the real numbers, P of xy equals 0. Well, yeah, this time we're making 0 be the first one. So yeah, this is true. This can happen. There is a special real number that makes this thing true. That special real number is x equals 0. In this one, the special real number is y equals 0. But up here, because it's for all x and for all y, we're not picking special ones. So it didn't work. Okay, now here, there exists an x and there exists a y such that P of xy equals 0. Yes, that's absolutely true. For the same reason the other ones are true. Given either x or y being 0, we're good to go. All right. All right, let's look at another example. This time, x divided by y equals 1. X divided by y equals 1. Okay, so I hope, based on the last one, you understand that the minute we start making for all statements, it's going to be a lot more difficult. We might be able to find an example that doesn't work. Okay? So, for all x, every real number and every y value, when you divide them, you equal 1. That's completely false. And I'm going to mention an example of where it's false. An example of where it's false is when x equals 4 and y equals 5. Clearly, when I take x and divide it by y, I don't get 1. But this says it's supposed to happen for every x I look at. Okay, and we're talking about all the real numbers, and those both are real numbers. So that would be an example of where this thing fails. And because it says for all, we break the loop. Okay, now we're saying for all x, so for every real number, there exists a y where they equal 1. There is actually a problem. Oh, I'm sorry, let me pause. So sorry about my dog barking. Okay. So we actually have an example that wouldn't work. There is a real number out there that the parent, you're not going to divide and get 1. And that real number is 0. X equals 0. It's going to come out 0 no matter what we divide it by, right?
So this is false. What we're doing right now is we're finding what's called counterexamples. And when a counterexample exists, like this, these types of for all statements, we're able to say that they are in fact false. In fact, let me just scroll back up here. And in this particular example, when it was false, the example where it's false would be when x equals 2 and y equals 3. There we go. That's false because those are two real numbers that don't multiply by 0. Okay. Now, there exists an x that when you pair it with y, every single real number, and you divide, you get 1. That's false. It's impossible. Because when you pick all the real numbers to pair with just one number, you're not going to be able to divide them and get 1 every single time. It's impossible. So the only statement that is in fact true is the last one here. This one is true. There exists an x and a y. A specific x, match it with a y, where this happens. Yes, that's true. Okay. So you can see the issues with the for all statement pairing up with the there exists. They sum this information up into a table, which I went ahead and included in the notes for you. You can reference that if you need to in the homework. But I want to kind of keep playing with this terminology and how we translate it into words. So they want us to translate the following into words. Okay, so here we go. Now we're working with propositions. So C of x means that x has a computer. F of xy, sorry, it kind of broke up onto the next line here. We highlighted it. F of xy is that the two people are friends, and the domain is students at the school or in your school. All right, so here we go. So for all x, so this is all the students. Not writing the translation yet. All students, okay? This says, for every student at the school, that they have a computer. Student has a computer. Computer. Or I just realized there's a typo. All right, I'll fix this. That should be C of Y. Or, there's another student and that's what the symbol, and that student has a computer. I'm not going to leave the translation like this. I'm going to clean it up, okay? Just kind of highlighting everything that we're seeing here. So here's what this really says to us. Every student at the school, so every student in your school has a computer. Or has a friend with a computer. So they either have a computer or their friend has one, so the implication being they could probably use their friend's computer. All right. Now they want us to, using the same labels, translate this one. Okay, so there exists, this first part here is a student. Okay. A student. And their saying for all y, so with this student, there's a bunch of other students, two different types of other students, okay? So there's a student who has a connection to all the other students. So that we're basically, we're basically comparing two other students together, okay? And either, or I should say and, the first student is friends with the second student. The first student is friends with the third student. And those two people are not the same. Okay, so there's a student out there who's friends with one student, friends with another student, and those two are not the same students. Okay. And we're saying that in this scenario, what happens is that when this is set up, it implies that the second student and the third student are not friends. So we're using the not symbol, right? The negation. So here's what we're saying. There's a student whose friends are not friends with each other. That's what that says. The student whose friends are not friends with each other. A little differently, they said there is a student, none of whose friends are also friends with each other. All right, let's try translating ourselves. Excuse me. The sum of two positive integers is always positive. I want us to translate this into a logical expression. So I believe they're making a distinction when they say logical expression versus quantifiers, in particular, like the propositional expression like we were just doing above. So I think we can write this using mathematics and not using the proposition language, the f of x, y's, or p of x, y's, or anything like that. Okay, so let's do this. The sum of two positive integers is always positive. Okay, so first things first, we actually need to define the domain here. So first thing I want to do is we're working with positive integers. So our domain is positive integers. First thing, we're looking at positive integers. And then all the positive integers, we can pair them up with another positive integer. So for all of them, as it says all of them, then x plus y is bigger than 0. That's how you can say that. Now, it is possible to not use u being the positive integers. If that's the case, if we just let u be the integers, all of the integers, then we have to make a statement about x and y first. So, for all x and for all y, where x is bigger than 0, and, oops, again, and y is bigger than 0, then space x plus y is bigger than 0. That's another way we can state it if we just want to do it with the integers. So now they ask us to use quantifiers, and we're going to do another translation, but this time let's use the propositional rooting, okay? So there's a woman who has taken a flight on every airline in the world. Okay, so first of all, we need to talk about the domain here and what we're referring to. Okay, so we have a woman, so we have W, and the domain for W, let's go ahead and say it's all women. There is a way to say that, but I'm going to try to say it kind of how the book would say. So the domain W is then you have the idea that they take a flight. Okay. So let's say F is, or I should say the domain of F. I'm not going to put a comma, I'll just list them. So I use F for flight, is all flights. Of course, we're talking about planes, right? And then we were talking about specific airlines here. So domain, okay, so we use A for airline. Is all, use this style A, is all airlines. Okay, so there's our domain. So we have three different variables that we're working with. All right. So let's define our propositions here. So let's let P of WF, that's going to represent that W has taken that flight. F is, and whatever woman we're talking about, we're saying that that woman has taken that flight. Okay? And then let's create another proposition, but this time relating the flights to the airlines. So in this case, we're saying that F is a flight on that airline A, whatever it is, American Airline, United, whatever, Spirit, I don't know if they exist anymore. Who knows? Okay, there we go. So we've gotten our three domains. We've created this language where we're talking about an actual person, in this case a woman that's been on a plane, and then we're talking about the planes and which airline they belong to. Okay, so now we're going to write the statement. There is a woman who has taken a flight on every airline. Okay, so let's start with the woman. And it's not a for-all statement. There is one woman. Okay? And this woman has taken a flight on every airline. So we want to start with the every airline. So for all of the airlines, there is a flight. Okay, that she, oops, I'm sorry, it's supposed to be an F, not a Y. There is a flight that she has taken. Okay, so there is a woman where we look at all the airlines and she's taken a flight with every single one of them. Okay, but now we have to say that too using our proposition. So we're saying then that she's taken a flight, and this is for all flights associated to the airlines. That's how we would make that statement. All right. So we're going to look at obvious predicates and express it as a logic. So we're just going to try to basically do this as simple as possible to create the simplest thing we can to write this in logic form. Okay. Brothers are siblings. Okay. So we're saying we don't need to define everything right now because you kind of saw what we did back here. In other words, if I hadn't given you these, I hadn't given this all to you, you might have been able to figure out what those represent based on this statement. Okay? You probably could have figured it out. So we're going to kind of assume the positional language without writing it out, but we could if we need to. All right, so here we go. We're talking about brothers and siblings. All right, so every brother, every time you're looking at a pair of brothers, they're automatically siblings, right? So we're looking at pairs of brothers, and they're automatically going to be siblings. This is how we write that. If you're brothers, then you're siblings. And this happens for every X and Y that satisfy that they're brothers. Because by putting the first statement, we're restricting ourselves to brothers only. And now we're able then to say that they will always fall into the sibling category. Okay? Siblinghood is symmetric. What that means, that's such a weird thing to say, sorry. What that means is that I have a sibling, her name is Angela, and she's my sibling, but she could also say I'm her sibling. So it's symmetrical. So we can say that we are each other's sibling. So we have this idea that we're siblings. I use the same label. Okay, that two people are siblings. Okay, then you can reverse the order with which you refer to the siblings. This is true for every two people who group up as siblings. So they're symmetric. That's what they mean by symmetric. Okay, there is someone who is loved by everyone. Okay, so we're using the two mix of language, right? We have this idea that there's an everybody and there is a single person. So there's somebody who's loved by everyone. All right, so the way we want to write this is there exists, a person out there. Sorry, there exists a person out there that everybody else is going to love them. That's what that statement says. Everybody loves somebody. Okay, so now this is saying that every person out there, there exists someone that they love. Everyone loves himself. Everyone loves himself. So every person out there, they're loving themselves. All right. And there is someone who loves someone. So there's someone out there who loves somebody else. There we go. That's how we would write that. Okay. So we created this expression earlier. There was a woman who was taking a flight on every airline. Okay, we wrote that earlier. So they want us to use quantifiers to express the statement that there does not exist a woman who has taken a flight on every airline in the world. Okay? So that means, first here. So I'm going to just step through this. So part A. So if I want to write that statement, I would basically just say there doesn't exist a woman. For all the airlines, there's a flight it's flying on. A member of all of the airlines. So that's how we would negate it, to say that there isn't a woman. Okay, so that's how we would do part A. Now, part B. Use De Morgan's laws to move the negation as inward as possible. Okay, so De Morgan's laws. De Morgan's laws, you might remember, basically starts flipping either if you're talking about and or, it's going to flip them. And if you're talking about these quantifiers here, then it's going to change them. Okay, so when you say that it's not true for everyone, that means there exists somebody out there. That's what that means. So they're wanting us to use that, right? That understanding of the De Morgan's laws. So let's start with this very first statement. When you say there exists no woman, there exists no woman, that means to say that for every woman, for all the women, okay, they can't have for all airlines where there's a flight that the woman took and is a member of the airlines. Wow, why do I keep doing that with the V? Sorry. That's how that looks. When you say that it's not everyone, that means there exists an airline. So all women. There exists an airline. There isn't an existing flight. Took. And there's a flight for for the airline. So what happens here when we apply a negation to a there exists? De Morgan's changes it to for all. Wow, sorry. All. So if there doesn't exist a flight, that means for every flight. So here we go. For all women, there exists an airline such that for all flights, now we're applying the negative in here. Didn't take that flight. This situation does not exist. And, oops, sorry. Should be applying the negative like this. Outside. We're going to apply it to the and statement. So I'm having trouble writing these parentheses. There we go. All right. So De Morgan's law over and statements turns it into or, but then both of these are now false. True, negated. So she doesn't take a flight. That flight is not associated to an airline. We're going to translate this back, by the way, here. It says, because man, that's kind of jumbled now. Trying to keep track of it. But whew, that was not an easy thing to keep track of. Okay, so this was part B. Sorry, I meant to call this part B. So part B. So now part C. Can you translate this back into English? And we're going to try. Okay, here we go. All right, so whew, for every woman, oops. Every woman, there exists an airline. For all of their flights. The airline's flights. There exists an airline out there for all of the flights the airline has taken. This woman has not taken a flight. Not taken a flight or a flight. Or the flight that the woman has taken is associated to a different airline. Not on this airline. It's a very convoluted way of saying that there doesn't exist a woman who's taken a flight on every airline in the world. But that's what it means. For every woman, there exists an airline, but all the flights for that airline, the woman has either not taken the flight, or if she has taken a flight, it's not with the airline that we're referring to. All right? Because we're saying specifically that there's a specific airline that we're able to pick out that she hasn't flown on yet. That's what this says.